So, what I want to talk about today is sizing pumps. But before we get into sizing pump, well, I guess first, before we really get started, does anybody have any questions from anything else that we've gone over since since I wasted a whole bunch of time trying to mess with audio? Anything come up? Anything you guys want to go over? Anything like that? No, everybody's good. All right, it's probably going to be. Well, I won't say it's going to be a short class. It shouldn't take us too long to go over this. I want to go mainly through selecting circulators, like I said. But before I do that, just another shout out to finding good manufacturer's manuals. I mean, every time you guys can, when you find something, get a hold of a manufacturer's manual and save them. Grundfos makes some good stuff. Takeo does some good stuff. A lot of manufacturers do some good stuff, train things like that. But anyway, this right here is just a Grundfos's pump handbook, and it doesn't have a ton of good information, but finding things like these just so you can go over, random stuff and learn things is always a good idea. So, we'll talk. Well, I don't know. We may or may not go through anything out of this, but I'm going to post this on Google Classroom so that you guys got this in case you want it. This is a little harder to find sometimes, and a lot of this stuff goes over. It talks in metric numbers a lot here and there. It doesn't go through pump head um, the same and feet of head and stuff like that. But other than that, there is information on the different types of pump curves in here. There's information on the different types of pumps you have and stuff like that. So, yeah, just something to go over in your spare time. I don't want to go over it today, but it's something you can look through. What I want to talk about is sizing circulators because a lot of guys don't know exactly what they're doing when they're trying to select a circulator, and I think it's just guesswork sometimes. So I try to make sure that I go over sizing circulators every year so that you understand what's going on. So one thing to note, all right, a lot of times, and I mentioned it last class, you'll hear guys talk about pumps versus circulators and things like that. When we talk about a pump, generally we're talking about something like a condensate pump, right? So on a condensate pump, you're going to have liquid in a reservoir, right? That you have to pump somewhere else or pump to the outside. And pumps are always rated in feet of head. Remember, 10 feet of head is about 4.33 psi, right? Um, so you'll have a condensate pump like your typical Little Giant. Will say it can handle, I believe they're 18 feet ahead. So, um, that means that the pump can basically handle pumping that water 18 feet up in the air, pretty much. Now, there's friction in the piping, but when you're talking about when you're talking about an actual pump like a ejector pump or a condensate pump, uh, the the friction loss in the piping isn't as big of a deal as the actual pump rise you have to get because you have to be able to pump that water up to 18 feet and out. If you exceed 18 feet, it's not going to be able to pump at all, or it's going to pump at a very low flow rate. So generally, the lower the feet ahead in the system, the more the pump can pump, right? The more the more volume it can pump. So, like that condensate pump, it might be able to pump 5 gallons per hour at 10 feet ahead and 2 gallons per hour at 18 feet ahead. I'm making those numbers up, but something like that. So with a pump like that, when it's actually being used as a pump, feet ahead, you can literally think about it as how high it has to pump up. But when we're talking about a circulator, it's completely different. All right. With a circulator, the the suction side is coupled to the discharge side. All right. So that means that the pressure, how high it has to pump, is canceled out by the fact that it's by the suction side is pushing down on it that much too. So let me see. Can I make a quick picture? Is it worth it? I'll give it a shot real quick. All right. So in other words, if you've got a pump, right? See if I can draw something quick here. I've got a pump and it's going in a loop. All right. The pressure it's got to pump up goes out of its feet ahead, right? With any pump. But the thing is since we're dealing with a circulator, the water is pushing down too. So, God dang it, I keep hitting the wrong button. The pressure's pushing down as well, right? So, since the pressure has to pump up, since it's counteracted by the fact that the water's forcing itself down on the pump as well, the feet ahead isn't really affected by how high it has to pump. Whereas if you're talking about something like a condensate pump, right? This pump, just draw a rectangular box for a condensate pump. It has to pump up, over, and out, right? So since it's going out and that side's not coupled to the pump, it has to actually counteract that pressure of pumping up. But when you're talking about a circulator, it's just going around in a circle. So the pressure is going to force itself down and up, so it cancels itself out. So when they talk about feet ahead when it comes to a circulator, the actual rise of the piping doesn't matter because it's one big loop. Does that make sense? Okay. So with a circulator, the um the feet ahead is actually the friction of the piping. Okay. So if you need to find a condensate pump that can pump up 30 feet, you're going to look for a condensate pump that can handle 30-foot ahead. If you need a sump pump for your basement and you need to pump that water up 10 feet, then you need a pump that can handle 10 feet ahead out of that pump. All right. But when you're talking about a circulator, the feet ahead isn't how high it needs to pump up. The feet ahead is how much friction it has to overcome in the piping. Now, like I said, in those other pumps, the friction in the piping still matters, but it's usually going to be minimal compared to the amount of head pressure it has to be able to pump. So again, that condensate pump that can pump 18 feet ahead, it can basically handle creating about 8 psi. You know what I mean? That pump can create about 8 pounds of pressure, and that's it. So it can't pump any higher than 18 feet because it can only create 8 pounds of pressure. Um, but when we talk about circulators, we got to talk about overcoming the piping. And when we're sizing circulators, it's the same as sizing anything else. So with circulators, the easiest thing to do is thinking of feet ahead as your static pressure in the system. It's the static pressure it has to overcome. So just like if you're sizing a fan for a house, if you got to be able to handle 1 inch static because your duct's long, Circulators, the same thing. You got to handle so many feet ahead because your piping's long. And you'll find as we go through this stuff throughout the year doing circulator sizing now, and then when we do gas pipe sizing, and when we do duct sizing, um, and anything else, it's we're talking about the pressure loss through the piping. We always end up talking about pressure loss somewhere, and it's not much different with a pump. It's the amount of friction we have to overcome, the amount of static pressure you have to overcome with the fan, with the gas piping, how much pressure you have to overcome in the length of your gas pipe. All those things. It's all about, what are we working against? So, Taco's article on selecting circulators is the best one I've ever found. And again, this will go up on Google Classroom, but it walks you through everything. When you're doing a circulator, it's important, like if you're replacing a circulator on a boiler, it's extremely important that you get a pump that has the same performance. So a lot of times those B&G, you'll usually see either B&G pumps on a boiler system, or you'll see Taco 007s or Grundfos or something like that. And those things aren't necessarily interchangeable. They're starting to come out with multi-speed. Grundfos has had multi-speed circulators for residential and small applications for a while now, and Taco's got a variable speed pump, which will handle things like that pretty well now. But if you're just, it's like anything else. If you're replacing a single speed pump with a single speed pump, then you need to make sure that it can handle the flow rate that you want and the head pressure that you have to overcome. If you have no idea what kind of pump a system needs, then it's important that you be able to size one. And I have ran into boiler systems before. I've run into boiler systems a couple times that they'll complain it's hard to get water to all the radiators, or it takes forever to bleed the air and they can't get everything, it never seems to work right. And sometimes that's just because somebody's replaced a circulator with the wrong kind. It could be there are instances in which, a baseboard's clogged up or a radiator's clogged up or something like that. But there are times I've found when the circulator just wasn't sized properly. So if you ever run into that situation, this is what I recommend as your point of reference for sizing a circulator pump in a boiler system, or for that matter, anything where you need a circulator. All right. I need to take 1 second, and I'll be right back. Sorry. All right. So before I start digging into this paper, any questions so far? All right. So we'll just read through it for a second, just to go ahead and cover it all the way. This article shows you how to select a TACO circulator that lets the hydronic system you're designing perform as expected. And this isn't only good for TACO circulators, but obviously it's a TACO guide, so gonna uh, they're going to go for their circulators. But this process works with any pump. As long as you got pump curves for it, you can go. So the process requires you define the flow performance of the piping system. After this, you'll match the system's performance requirements with the circulator that can supply them. It's much like defining the performance requirements of a car, then selecting an engine capable of delivering that performance. So you already need to know the BTUs you want to put out in the system, how fast you want the water flowing through the system, Well, you're gonna find out the flow rate, but you already know you need to know how many BTUs. So if you got 100,000 BTU boiler, you need to know you need that size boiler. And the other thing you'll need to know as we get down here is the temperature drop in the circuit. So it's pretty common to go for a temperature drop of 20 degrees. I will say this. I mentioned it a little bit last class, but for higher efficiency boilers and things like that, it's usually not a bad idea, especially if you're going to be running at a higher temperature, to have a slightly bigger temperature drop sometimes. The colder return water temperature helps out in their efficiency. Um, but in general, a lot of systems are designed for a 20-degree or so temperature drop. It's a good idea to look at your boiler specifications too, though, because depending on your boiler, they may want a specific delta T across the boiler. So, if you've got a system with a large temperature drop, sometimes the boiler will require a bypass in it so that you can have a slightly less of a temperature drop. So for instance, I've worked on lock-in bars before where they wanted a maximum. I can't remember the exact number, but say they wanted a maximum 15-degree temperature difference from the return and the supply temperature of the boiler. So if you designed it with a 20-degree temperature difference, you would need to bypass some of the supply back to the return to maintain the minimum temperature difference that they wanted. So it's important to keep that in mind. Sometimes your boiler specifications will call for a maximum difference between return and supply because of the heat exchanger design. So keep that in mind. But anyway, if you don't know, then 20 degrees is generally a good starting point. All right, so the target is the flow rate you'll expect under design load conditions. The flow rate depends on both the rate of heat transfer needed and the temperature drop of the piping system as it delivers this heat transfer. Keep in mind the actual flow rate at which the system operates may not be exactly equal to the target flow. It should, however, be relatively close, within plus or minus 10% of the target flow rate. And that comes up a lot in our trade, right? Plus or minus 10%. Plus or minus 10% on voltage, plus or minus 10% on airflow, CFM delivered to individual rooms, and depending on your system, even your system, you're going to see plus or minus 10%. That's what we're trying to get to. We don't have to be exact, but we want to be plus or minus 10% when we design it. So for systems using water, the target flow rate can be calculated using the following formula. So F is our flow rate, and that's going to equal Q, the rate of heat transfer, so that's your BTUs per hour in the system, right? Divided by 500 times our delta T. All right. If the fluid is 30% glycol, change the 500 in the formula to 479. If the fluid is 50% glycol, change the 500 to 540. So if you got glycol in the system, it actually does not transfer heat as efficiently as water does. So pure water always transfers heat better. But obviously, if you got glycol, it's there to protect it from freezing. So a lot of times you'll be between a 30 and 50% glycol solution to keep the system from freezing in case it gets cold it comes in contact with really cold temperatures. So the reason that number changed is because 500 is basically a constant for how well the fluid is transferring heat, and the more glycol you have, the slightly less efficient that fluid will be at transferring heat. So in this example, we'll look at a hydronic distribution system being designed to deliver 100,000 BTUs under design load conditions. The system fluid is water, and the expected temperature drop at design is 20 degrees. What's the flow rate required? So if we wanted a 20-degree temperature drop for a 100,000 BTU system, then we're going to do F 100,000 divided by 500 times 20, which is going to be 10,000, and that's going to be 10 GPM. So in this case, we want a pump that can handle 10 GPM. So although it's customary to design hydronic circuits with the target temperature drops of 20 under design load conditions, There's nothing magical about the number 20. Many systems can be designed to operate with higher temperature drops. The greater the circuit temperature drop, the lower the flow rate needed for a given rate of heat transport. Lower flow rates are often lead to reduced tube sizes and smaller circulators. And this is kind of why, depending on the system, guys can get away with just, there's a B&G pump in there with these performance characteristics, and you switched it out for a Takeo 007, which is a pretty common pump, right? So the reason they get away with that, even though they didn't make sure that the pump curves were the same, is they basically just changed the temperature drop in the system. Unfortunately, you're not always going to get that lucky. I would say probably 5, 6, maybe 7 times out of 10 on a residential system, you can just get away with that. But in those cases where you can't, where the pump you put in can't handle the head pressure drop throughout the system, or can't handle the flow rate that you wanted on especially cold days, um, the system's not going to perform well anymore. So you just putting in the wrong circulator there just completely made it so not everything operates good anymore. And that's why being able to size a circulator is so important with a boiler system. So in this, it talks about selecting the tube size. And we are going to talk about selecting the tube size. So this is where if you're actually designing the boiler system from scratch, you can dictate what the tube size needs to be at the beginning. If you're working on an existing system, you need to look at the tube size that they already selected, and you need to try to estimate kind of how they ran the piping. And I know that can be kind of difficult sometimes because you obviously can't see into the walls, you can't see into the ceilings, what they used where. But if you pay attention to how systems are piped, then you'll be able to get a good estimate about how far they ran and how many fittings they probably have. Um, you can get a really good idea of how the systems run. And it's probably a little more difficult if you've never ran a boiler system or seen a house with the entire system out. And we're going to, at some point, probably next class, I don't know if we'll get to it tonight, but at some point we'll talk about the different ways that a boiler system might be piped, but it's generally not that bad. But just checking out the tube size and having an idea of how they piped it can usually give you a good idea of what you're going to be dealing with. Um, but in this case, we're going to talk about it as if we're selecting it from the beginning. So once the target flow rate has been established, the tube size can be selected based on flow velocity limitations. Select a tube size that keeps the flow velocity in the tube in the range of 2 to 4 feet per second. The lower end of this range provides sufficient velocity to entrain air bubbles and carry them along until the flow passes through an air separator. Flow velocities lower than 2 feet per second may not entrain larger air bubbles, especially in downward flow through a vertical pipe. The upper end of the velocity range keeps flow noise at acceptable levels for tube passing through, above, or below occupied space. And the other thing that to keep in mind is as the velocity goes up, if you try and size at a higher velocity, not only does the noise go up, but your pressure loss is going to increase. And think of it as it's moving faster, you're going to have more friction in the pipe essentially. So generally, you don't want to figure then more about 4 feet per second inside the pipe, and we're going to talk more about that shortly. So table 1 can be used to select sizes of type M copper tubing as well as PEX L PEX. Um, PEX or PEX L PEX, I think. Let me look at that again. All right, so yeah, M copper tubing as well as PEX and PEX L PEX tubing based on these limiting velocities. Example 2, assume the target flow rate of 10 GPM from example 1, and the copper tubing is used for the circuit. What is the proper tube size based on keeping the flow velocity between 2 and 4 feet per second? I notice here they have some more technical docs, I don't know if I've ever looked at their TD09 understanding pump curves. Maybe we'll try and pull that up after we're done here. All right. So look at the answer. Look at the copper tube sizes in table 1. So these are your tube sizes. And I know it doesn't show black pipe here, but black pipe is relatively close to copper. So you can use that as an estimation if you're using black pipe. All right. Black pipe is going to have slightly more loss. It's going to be slightly below this, but I found that if you figure copper there, it's pretty close. All right. Um, So look at the tube sizes, find a size for which the target flow rate of 10 GPM falls within the values of the second, third column. In this case, 1-inch copper tube meets this condition, and so does 1.25-inch copper tube. So we said we needed 10 GPM, right? So we have 10 GPM is between the minimum and the maximum flow rate right here. And let me, right there. Right there, 1-inch copper is between 5.5 and 10.9 GPM. So that's kind of our range of flow that we can have through copper. And then right here, 1.25 is 8.2 to 16.3 GPM. And by the way, this is a pretty good estimation of how much flow you can get through a pipe. Okay, so if you're working on a water source heat pump, or you're working on a coil, and you need so many GPM through it, and you're thinking, well, maybe they sized the tube too small. This little table here is pretty handy for you can do the math for it, but this is pretty handy table if you're not used to it. For going, okay, well, how much flow can I get through a 3/4 pipe? If it says it needs 4 GPM, can I get 4 GPM through a 3/4 pipe? And yeah, we're within a range for 3/4 pipe on GPM, and so on and so forth. So if you ever wondered how many gallons of water you can get through a pipe, you can get a lot more than this on a higher pressure plumbing system sometimes, but these are still pretty good GPMs to figure on anything that's circulating. So anyway, either one will work, right? So the 1.25-inch tube would generate less head loss than the 1-inch tube. So as the pipe gets bigger, we're going to have less head pressure losses through the pipe. There's less friction for the volume of water. Okay. Um, this might mean a smaller, less expensive circulator. So the less the head loss, the less powerful the motor on the circulator has to be. So it's going to be a cheaper circulator. On the other hand, 1.25-inch tubing is more expensive to install, right? If you need to run 200 feet of this pipe, then there's a difference between 1 inch and 1.25 inches. And I know it seems like a small point, especially if you do service a lot or something like that. Is it really that big of a difference? Well, I mean, it can be. So generally, you always want to strike a balance with what you're doing. So the 1.25-inch pipe is going to be more expensive up front. So to make an informed decision as to which tube size is best, you can follow the remainder of the procedure assuming 1 inch, and then repeat the procedure assuming 1.25 inches, and then compare your results. This is the only way to know that if the larger tubing would allow a smaller circulator to be used. So you might get to the end and you'll need the same circulator either way, in which case why not go 1 inch, right? But you might get to the end and find out, oh, I need this pretty expensive, hard to find off the shelf circulator, so it's not worth using the smaller pipe at that point. So based on that outcome, you can figure out what you need. So the next part is finding the equivalent length of the piping circuit. So to find the equivalent length, you do this in refrigeration, right? We especially do this in gas, but we'll talk about how long your run is on your refrigeration circuit when you're sizing refrigeration piping. And a lot of times people don't factor in the fittings, but the fittings technically matter, right? One elbow is like 5 feet of pipe or whatever. So we need to find the equivalent length for the piping circuit when we're talking about a boiler system too. The only thing is in a boiler system, the links for the fittings matter a pretty reasonable amount, especially when you're talking hard copper 90s or you're talking steel 90s or something like that. So we got to figure out how far we're going to run the piping circuit, how many T's are going to be in there, and all that. So you have to have a sketch of how you want to run the piping, or at least a good idea of how it's going to be ran. And then you got to find the equivalent length. So table 2 lists the equivalent lengths of common fittings based on their size. To get the total equivalent length of the circuit, add the equivalent lengths of all the fittings and valves to the total length of straight tubing. So, example 3, a piping circuit consists of 150 feet of 1-inch M copper tubing, as well as 25 90-degree elbows, 3 side port T's, and 4 ball valves. What is the total equivalent length of the piping circuit? The equivalent length of the 1-inch fittings and valves is found in table 2. So here's the table they're talking about. And you can see for 1/2-inch pipe, we have equivalent lengths for everything. 3/4, same thing. 1-inch, same thing. So before we finish this example, I want to point a couple things out in this table. Does anybody know what a Venturi tee is? Yep. Anybody familiar with a one-pipe boiler system? Yeah, so a one-pipe boiler system is going to have the Venturi tees where the supply and return come back to the same line, right? Because there's a single loop. There's one single loop, and everything just circulates through a single loop. There's no return line and supply line. The supply line just goes in one big loop back to the boiler. So on a one-pipe system, you only have to run a single pipe, but um, you got to have those T's in there. And if you look at the equivalent lengths of these Venturi T's, a 3/4 Venturi T is 28 feet. 1-inch Venturi T is 19 feet. So those add up pretty quick and, increasing the increasing the head loss on the boiler system. Globe valves. So globe valves are, if you're familiar with any commercial stuff, um, your balancing valves, like who makes them? Victaulic. Victaulic makes balancing valves that are built like a globe valve, and those have a very high head loss. They're very the equivalent length of pipe, for a 1/2-inch globe valve is 17 feet. For a 3/4 globe valve is 23 feet. So it adds up. Zone valves can add up. Your 570 series zone valves, a Taco, is 10, 20, 60, 130 feet. The 1.25 inch zone valve equals 130 feet of pipe. So it can be a large head loss. Things like that, you need to pay attention to a lot. Where you have those kinds of items in the circuit, they're very big spots for a lot of head loss. So keep those things in mind. Everything else is kind of just nickel and diming you. 90-degree elbow, a 3/4 90-degree elbow is 2 feet each one. So it's not that much more. But if you have a bunch of them in the system, it's going to add up. Your T's, if branch flow, so they have T's through flow and branch flow. If you just go straight through the T for the main run of the circuit, that's 1 feet, right? Or 1.3 feet. If you're gonna 90 in the you have branch and run of the T. So if you're looking at a T, right? There's your run, there's your branch. If the run is continuing the loop back to the boiler, right? So if you got a T here going to a radiator, and that's continuing that's just, and the flow just continues around the path, that is a straight run T. A branch T would be if, so that would be a run T. A branch T on the table would be if you need to continue the loop this way, but you're catching a radiator that way or something. So in other words, it's the water's going to kind of favor just continuing up through the it's going to just favor continuing up through whatever appliance you have that way instead of maintaining in the loop. So that's what they're talking about there, through flow versus branch flow. So anyway, the example goes on. So the total equivalent length of the circuit is 25 times 2.62. So we're talking about 1-inch pipe, right? So they're saying 25 times our 1-inch 90s. So that's this one, 25 90s, right? At 2.62 feet per 90. Then we have 3 side port T's. Equivalent length for each T is 5.25 feet. So they're talking about here, they're doing side port T's. And then ball valves, the equivalent length for each ball valve is, they said 4 ball valves, right? And we see our ball valves down here, 1.8 feet each. And so, and then we have 150 feet of straight pipe, all right? So the 25 times 2.62 plus the 3 times 5.25 plus the 4 times 1.8 plus our 150 feet gives us about 239 feet. So that would be the equivalent length of the piping circuit. All right. So once you've got the equivalent length, we can determine the head loss of the piping at the target flow rate. So in a system with multiple zone valves, the head loss needs to be calculated for each parallel loop. This is very important right here. The loop with the highest head loss, all right, is going to be the total length. So this is the same. Let's see if I can grab, will a highlighter work? Yeah. All right. So this is the same for any system pretty much. So when we're sizing duct, when we learn about sizing duct, we're going to talk about the largest loss, the longest return line, and the longest supply line. Same thing with this. If you have multiple zones, your total equivalent length needs to be placed on the farthest zone. So if the house is one big zone, then it doesn't matter. You just go your longest, you calculate everything in the zone. If you have 4 zones, you'll have to find which zone has the most head loss, has the longest equivalent length, and use that as your basis. You won't add all the zones together, because as long as the pump can handle the longest zone, the one with the most equivalent length, then it can handle the smaller ones. And that's the same for everything else. Like I said, this is kind of a good primer on looking ahead to how we design other things. The formulas are a little different because we're dealing with water as a fluid instead of air as a fluid. Our pressures are going to be different, which affects how these things are calculated, but everything is pretty much the same. So far we've gone over knowing how much flow we want, right? Figuring out how big our pipe's going to be, mainly so we can figure out the equivalent length, so the longest run. And then we're going to establish, okay, what's that pressure that we have to work against based off our longest run. So the formula for estimating head loss for piping circuits constructed of smooth tubing such as copper PEX or PEX out PEX is this. All right. So this is our formula. Our head loss, what we're trying to calculate, head loss is what we're trying to find in feet of head, all right, because everything's in feet of head. K is a number based on the tubing size, so you have to find that in table 3. Oh, that's table 2. You have to find that in table 3 right here. So this is just a constant, all right. K is just a constant based on your tubing size. C is a correction factor for the fluid type and temperature. That's just a constant for the temperature you're going to run at and the type of fluid you have. This is basically a density correction, okay? So C is a density correction for the fluid. So different temperatures change the density of water. glycol changes the density of the fluid in it too. All right. L is the total equivalent length of the piping circuit. That's what we just learned to figure out, right? And F to the power of 1.75 is the flow rate of the piping system up to the 1.75 power. So that just tells us, okay, how fast is the fluid moving through it, right? So based on all these, this is going to account essentially for the extra friction of the water moving at a high speed. All right, so find the head loss of the piping system having a total equivalent length of 239 feet, 1-inch M copper, and operating with a water at an average temperature of 140 and a target flow rate of 10 GPM. So we figured out we have 239 equivalent feet of pipe in the previous steps. We know we want 10 GPM at the previous steps, and the temperature of 140 is what you're going to pick based on your system. So you would actually find that number in the real world. You would determine that based on, so if you were selecting radiators, it'll say this size radiator can handle this many BTUs at 180 degrees and this many BTUs at 160 degrees, and so on and so forth. Obviously, the lower temperatures are generally going to end up being more efficient, especially with if you're talking about condensing boilers and stuff like that. The lower the temperatures you run at, the more efficient it can run. Um, but a lot of times it's just based on what you're working with. Designing at a higher temperature will let you use smaller baseboards, smaller boilers, um, less loops in your radiant heat. But lower temperatures will be a little bit, you can design the system more efficiently, but you'll need bigger radiators, bigger baseboards, things like that. So in this system, they're designing for 140, which is a pretty common temperature, right? So the K value for 1-inch copper from table 3, so you just take this value and plug that in for K, is 0.000845. So you plug that in here. The value correction factor from table 4 is 1. So 1 is our baseline, basically, right? They base all these numbers off of a standard density of 140 water at 140 degrees is our 1, and then as the temperature changes, it goes up or down from that. But this is basically anything is going to have some kind of baseline for its density, and they're using that as the baseline in this formula. So that would be 1. 239 is our equivalent feet, and 56.234 is 10 to the 1.75 power. So you add all those up, and that's 11.36 feet ahead. So now we know how many GPM we need and how many feet ahead we have to work against. So the target operating condition of the piping system is 10 GPM at 11.36 feet of head. The head loss is the target operating point for the system. All right. So now you just got to select a circulator. So this graph is kind of neat. This is obviously all Taco pumps, right? You'll look at, you can use any pump manufacturer's curve though. These are all just different pump curves. So what they're showing on this chart, right? If you're familiar with Taco circulators, then you know you can probably recognize these numbers. They have a 007 pump. That's a pretty common pump. All right. A 009, but they got a bunch of them. You got 0012. All right. 0013, 0010, 003, 006, 008. 008's pretty common too. So these are all your different pump types. So these are all curves for different pumps, and I kind of wish they'd make this thing in different colors to make it easier, but it is what it is. Maybe I'll go through and color this graph one day so it's easier to see, but these are all just different pumps. So you plot the target operating point on the graph showing the pump curves that you're working with, and a lot of times you're doing this, you'll actually pull up the pump curve for just the 007 and the pump curve for just the 0012 or the pump curve for a B&G model, um, I can't think of one right now, but a B&G pump or a Grundfos pump or whatever it is. You'll pull up those pump curves and then you'll look at that curve and you'll put wherever you need that pump to perform on here. All right. So right here, this is the operating point that we're dealing with. Okay. Right there. Oh, no, that's not what I wanted. All right. So anyway, this operating point right here. So you plot your operating point on the graph with your pump curves, and then you look for a circulator with the pump curve passing through or close to the target operating point. So you want something that operates very close to where you want it, because this is the operating curve for the pump, right? This pump isn't going, it's going to be hard to get this pump to pump exactly where you want it because that's not on the pump curve. So you try and get one as close as possible to the pump curve. And we'll look here at 0012, right? Is very close to the operating point. And a 0010 is pretty close to the operating point. So uh, we can see the 0010 right here. We can see the 0012 right here. All the other ones are a bit farther away. This 009's kind of close, but not really. And the 008 is kind of close, but not really. So because the curve for the 0012 is slightly above the target, uh, the system flow rate will be a little bit higher than your target value. So you're going to have slightly more flow if you put in a 0012 than you calculated for, but slightly more is generally better than slightly less, right? Generally, within reason, having a little bit of extra head loss, if they added 5 more 90s in there than you designed for, or you're not sure how many 90s there are in there if you're reverse engineering the system and you're trying to make sure that whatever pump you put in is going to have a little bit of wiggle room, then you want to make sure you pick with something that's slightly higher. And that gives you, it just says right here, it's not necessarily a problem. It means you got a slight safety factor to cover slightly greater installed pipe lengths or other unforeseen conditions that might increase system head loss. Think of it as selecting a boiler that has slightly more heat output than the design heating load. We select a boiler if we need 40,000 BTUs. We're probably not going to select a boiler that outputs 40,000 BTUs. We're allowed to size up to 35 or 40% over on them. So we're going to select something that's got a little bit of extra heat output. And that's acceptable with gas appliances, but that's another class. The pump curve for a 0010 passes just under the target operating point. If the circulator were selected for the flow rate, and the flow rate and system would be slightly less than the target flow rate. If the drop in flow was limited to no more than 5% of the difference, and the system's thermal performance would be negligible, and thus the smaller circulator might still be a suitable selection. So if you're going to go below it, you want to make sure that the loss is no more than 5%. That basically gives you another 5% of wiggle room for your plus or minus 10%. So, however, it's generally considered poor practice to select a circulator that yields flow rates less than the calculated target flow rate for the system. So another option you could do is investigate before you pick the circulator. If you're designing a system from scratch, you can say, all right, well, what if I use 1.25 inch instead of 1-inch pipe, right? And it basically changes all your calculations starting at step 3. So if you use 1.25 inch instead of 1-inch, so if you're like, I don't want a 0012 or 0010, those are high head loss pumps. If I go with 1.25 inch instead of 1-inch, and we redo all those calculations. So you plug in the number for 1.25 inch, times 1 times our 239 feet times our 56.234. You can plug in that new number and say, okay, the head loss decreased significantly because we're using 1.25 instead of 1 inch. The system's target operating point is now 10 GPM with an associated head loss of 4.35 feet. So we went from, where's that? We went from 12 feet ahead, right? That's what we were at. Just double checking. Yeah, we went from basically 12 feet ahead to just over 4 feet ahead by going from 1 inch pipe to 1.25 inch pipe. All right. So the head loss decreases significantly just on one pipe size up, and you're still operating at 10 GPM, but now you got a head loss at 4 feet. So you can replot that point on your graph, and you'll be right here instead. I think I got an arrow. Nope. So that's the second point, and that's the first point we had, right? So on the second point, we can see that we can use a 005 or a 007. So if you look at it, the 007 is here, all right, which is a very common pump, and their 005 is here. Dang it. Five's right here. So both these pump curves are close to that then. And so it falls below a Taco 005 or 007. Those are less expensive circulators and they use less energy. So if you're talking about energy efficiency, like I said, you use bigger pipe, it's generally going to be more efficient. You use bigger duct, you're going to have less static pressure in a system, right? Um, so when it comes to something where you've got a circulator or a fan, generally the bigger you can make the pipe, the better. The bigger you can make the duct, the better, up to a certain point. Again, we want to have a minimum velocity in both cases a lot of the time, but it's usually pretty hard to hit that number. So, um, so then you can use a smaller circulator, and in combination, the 1.25 inch pipe size, you'll lower the overall life cycle cost of the piping system. And that's the other thing to think about when you're designing something is the initial cost. So 1.25 inch pipe costs more upfront than the 1 inch pipe. So it's going to cost the whoever's buying the system, is going to have to pay, $1,300 instead of $1,000 or whatever the case may be. Okay, so it cost them $1,300 for the system instead of $1,000. But that 0012 pump, I don't know how much those are, but say that's a $300 pump. All right, so it really is going to cost you $1,300 for the $1,000 system, and then but the 007 is only $100, so it's $1,400 for the 1.25 inch system at that point. So now we're closer in cost, right? But in 10 years, 5-10 years, when they have to replace that pump, it's going to cost them $300 every time they got to replace the pump, as opposed to the 007, it'll cost them $100 every time they have to replace the pump. So you're lowering their overall life cycle cost of a system. And generally, you're figuring on a boiler system, you should figure that system's probably going to last 40 or 50 years at least. All right, boiler systems go for a pretty long time if everything's held in pretty good shape. So you want to figure about a 40 or 50-year life cycle cost at least for a system like that, if not 100 years. A lot of systems are designed in buildings to last 100 years if possible. So you have several choices at this point that can satisfy the target flow rate of 10 GPM. The final decision depends on weighing the cost differences along with your preferences. No one circulator is necessarily it's not going to be one choice. All right, there's not only one choice that you can choose from, but you need to kind of weigh your options when you're selecting it. And again, I know a lot of you guys probably aren't going to be designing systems on a regular basis, boiler systems, but we're going to learn to do load calcs this year. It's very possible you'll be designing a boiler system at some point in your career. But even when you're doing replacements, having a good idea of how the pipes run in the system, all right, and you already know, you're going to know the pipe size because you'll see what the main size is coming back to the boiler. I'll bet you a dime to a dollar if you just pay attention, you can guess how that zone is ran because you know where the piping starts in the boiler system. You'll know how many radiators or baseboard heaters or air handlers or whatever it may be that are off that boiler system on each zone. So you'll have that information. That tells you probably how many T's you have, right? Because you're going to have to have a T for each one of those in the system. If it's a one pipe system, if it's a monoflow system, then you'll know how many Venturi T's you're going to have in it. You'll usually see most of your ball valves and stuff, right? You'll know how many ball valves you'll have in there, and you can guess how many elbows, to get to that pipe. How did they run it? Well, they had to have ran up to the first floor and in the second floor, in the ceiling above the first, right? So they run in the ceiling above the first floor, and they, based on where the pipe runs, they probably went around in this loop and then came back down. You can take a pretty good guess to how many 90s are in there and then add a few to be safe, and you can estimate what your head loss is going to be in the system. So it's pretty easy to do that. You don't even really have to measure some kind of head pressure or anything like that. You can do it if you get the equipment, just like airflow. You can actually measure how many GPM the pump is pumping and do it like that. But a lot of times with boilers, it's just as easy to say, okay, about how many feet of head loss do I have in this system? Based on that, what size circulator do I need, at the GPM that I want, which again is usually just going to be based off a 20-degree delta. And you go from there. So, one thing I'll promise you guys is that I will not make you size a pump. So, most of this information we just went over, I won't test you on it. But it's very good information to have in the back of your pocket, so that if you ever have an issue where you think a pump's too small for a boiler system, or you are designing a boiler system, um, we go through a lot of sizing um, air handler systems, and stuff like that. But it's not often that we'll go over, sizing a boiler system throughout the year. But sizing a boiler system is pretty easy. You look at the specifications for, your radiant floors or whatever, and you figure out what size boiler you need based on your load calculation, and you size your circulator. Use that system to size your circulator, and you'll be in good shape. All right. Any questions? Um, no, actually, I have no idea if there's a large difference. I've not, but it's an interesting question. So ethylene, let's see if we can find something. Ethylene glycol versus polypropylene. Yeah, or propylene, polypropylene. Why did I thinking piping, not glycol. All right. So yes, propylene glycol is environmentally safe and it's non-toxic. Okay. Ethylene glycol is toxic and it is not as environmentally safe. So in general, if you're doing glycol from scratch, it's generally recommended that you um, go with propylene instead of ethylene anymore. But it is a good question. If you switch glycols, are you going to change the heat transfer? So your overall heat transfer coefficient for propylene versus ethylene is a little bit less. So it's not a lot. I mean, we're talking about a 0.25 versus a 0.22, and I don't know what the baseline is for water. That's what I would have to find out. Um, yeah, and it depends on the percentage, right? So, trying to see if I can find anything that gives me a good relationship. So I'll save this and I'll throw it up for you guys. But it's my understanding, based on how close these are together, and again, I don't know where one is at a reference, I don't think that you're going to affect the system enough to worry about it. And to be honest, boiler systems are generally way oversized. All right. Especially if you're dealing residential, your boiler is probably almost twice as big as it needs to be. It's at least 1.5 times bigger than it needs to be, and it's probably oversized even more than that. Commercial, you might be a little bit closer, but commercial usually has a bigger diversity in the loads, right? So the odds of everything running at full tilt on that boiler system are actually pretty small, even on a design day. So I really don't think it's enough of a factor to worry about. But technically, propylene is a little bit less efficient than ethylene. Hmm. Right. Hmm. Yeah. It would be interesting to look at one that's been switched from ethylene to propylene and say, okay, does this one with similar units on it, does it actually have that much of a performance difference? Because with AC, a couple percent can be a lot if you're talking about AC. A 2% loss can make a big difference. Sometimes it's not a huge difference, but it's still, it's a good few hundred BTUs. And a lot of times we're only dealing with, you know, 100,000 BTUs or something like that on, or whatever, 50,000 BTUs. So the little bit can make a difference. Um, yep, and that appears to be accurate. All right, I'm going to save this too, and we're going to open this up in a second because, like I said, I don't think I've actually ever read this technical paper. So we can look at understanding pump curves. All right, so understanding pump curves. Oftentimes, someone will walk into a wholesaler and ask for a pump that can produce 10 GPMs of water or can lift water in a system's tank that's 20 feet tall or two-story house, right? Or is the correct size to match a particular boiler. Although they're reasonable questions, none of them are sufficient to select a proper circulator for the situation. Selecting a circulator requires an understanding of the circulator performance, and this describes one of the most basic indicators, the pump curve. So I'm not going to read through this whole thing, but I will go down, and this is a pump curve, right? So this is just another pump curve. So remember, we were looking at the 007 pump curve on that other chart, but this is the actual pump curve for just the 007. And remember that other system where the 007 was close, that system was 4.3 feet ahead at 10 GPM. So we were like right here on this 007 pump curve. All right. So you look at that pump curve and you'll move along the curve. We got another picture here to go by. All right. So you'll have the shutoff head, right? This is the pump curve. Shutoff head is the end of the curve over here, right? So once you get over 10 feet or 11 feet ahead on a 007, it basically won't pump anymore. Okay. It's going to freewheel at that point because you're just more head than it can produce. That pump can basically only create about what 12 feet ahead. It can basically only create about 5 psi, say, and you're over 5 psi. So the pump can't create more than 5 psi worth of head pressure. So anything over that, it's just not going to do anything. All right, that's the shutoff head. It's just going to deadhead basically. Um, so you've got that. And then down here, basically, if you get past that on this end, then, the pump's not working against any pressure at all. So it's basically just like having the pump run open on the end. It's not going to be very efficient. Generally, your efficiency is in the middle of your pump curve, too far this way, and the motor is just spinning too fast and not doing anything. And up here, it's working too hard. Um, and then you have the system curve. So this is um, this would be where the operating system would be at, right? So as you move down along the system curve at 4 feet ahead, you're going to be moving at 6.5 gallons or so per minute. And then if you go up in feet ahead, up at 14, you're going to be running about 12 gallons per minute. Um, so anyway, you need to select a pump where the system curve is within your operating point. And then do they go over efficiency curves? No. The other thing you'll have in here sometimes is your actual efficiency curve. So it'll tell you where the pump's most efficient. And in the Grundfos book, it shows you that. So a lot of times pump curves will have um, a an actual head curve and then an efficiency curve, and what's the other ones? This is the Grundfos one. See if I can find this real quick. Dang it. Come on. Got the pump curve, you got an efficiency curve, and then you'll have the head curve. So it's part of the pump curve basically. And then power consumption. So the actual power consumption of the pump based on how much you're going. And then net positive suction head is basically where you need to be before you hit cavitation. So sometimes they'll put charts together that have all those curves on one chart, so you can kind of make a good, like this. You can make a good, you can have a good idea of, okay, what's my power consumption going to be, and my net positive suction head going to be at the operating point of the system right here. The efficiency, so you can see like this one, it's just a little bit past the best efficiency, and the head curve, how much head you're running at. So yeah, pump curves. I'll put that on there and you can read this whole article and that'll help you a little bit. But we won't actually cover that now because we don't have that much time to read a whole nother paper. All right. Um, any questions so far on that? All right. Last thing I wanted. No. All right. Last thing I wanted to talk about real briefly is your connecting piping to your pump. All right. I talked a little bit about it in the last class, but I want to expand on it a little bit. This is normally the day that if we were doing class in person, we'd walk down and look at the boiler room in the school so we can talk about how to properly pipe to a circulator. But we are going to just look at a picture right for now. And not that one, this one. When you're talking commercial or even large residential, things like that, um, or you're dealing with an end suction pump, a lot of these concepts are important even for inline pumps. So no matter what pump you have, these piping principles are important. On a circulator pump, the things that you generally want to have in the piping going to and away from the pump are a valve on the suction side, and that's just for service. It should never be closed at all, any amount, unless you're servicing the system. But if at all possible, having a valve before the pump is a good thing. A strainer, you have a strainer before the pump is generally a good idea to keep anything from getting into it, but you need to be very careful putting a strainer before the pump, okay? Because strainer is going to block flow to the suction side of a pump, and you never want to completely block or cause enough restriction in the flow that you end up cavitating. So if you do a strainer before the pump, it's extremely important that it's maintained and that it stays clean. If you are unsure, the best thing to do, don't put a strainer in the pump. Okay? It's not a bad idea to have a strainer, but if you want to err on the side of caution, it's better to have a pump damage from large debris in the system than to have a strainer and the pump cavitate, because the odds of you getting large debris in a closed loop is usually pretty small compared to the other problems. So with a small inline pump, small circulator, I would not recommend a strainer. On big commercial systems where the possibility of large debris is a little bit higher, you'll see strainers on the inlet side of the pumps. You should have a flex connector, if at all possible, before the pump. That just helps isolate the pump from the piping system. You see a lot of pumps leaking at their flanges. Anybody ever notice that? Yeah. Pumps leak at the flanges a whole lot, don't they? Partially because a lot of times there's no flex connectors in there. All right. If you got no flex connector on the pump is going to transmit. It's going to transmit that vibration into the piping system. And where those things are connected, you're going to increase the possibility of leaks. Honestly, compressors are the same thing. Really, it would be great in AC systems if we had flex connectors on compressors more often. And on large AC compressors, you will see flex connectors because compressors transmit vibration. Anything that's connected to piping is going to transmit vibration to the piping unless you have some sort of flex connector there to absorb that vibration. So even on small residential, it's not a bad idea to have flex connectors on your pump. Then you'll 90. Hmm? Yep. It's very common on bigger stuff. Um, Now when we get to here, if you're talking about an end suction pump, so it looks like this. All right. So this an end suction pump is one where it's mounted horizontally. You're going into your suction on the bottom horizontally here, and then it pumps up out vertical. If you're doing an end suction pump, you get a 90 over into the suction side a lot. If you're doing an inline pump, this is going to go straight through. Either way, on the suction side, whereas I think this is the right button. All right, no, that's not it. Looking for something. All right. the dimension from here to here, all right, should be 10 pipe diameters. So if this is 3-inch pipe on the suction side, you should have 30 inches between a 90 and the pump. Okay. This, even on inline pumps, having good straight pipe before the pump is important. So you need at least 10 pipe diameters before the inlet of a pump. And that's going to make sure that you have a much smaller possibility of cavitating. And again, even on the smallest, I think they're like 002s or 003s or something that they use on circulating lines for hot water, for domestic water. They use, those small circulators. Even on those where they have a 90 going straight into the pump, I've seen those pumps cavitate like crazy. You can just hear the pump cavitating, but it's such a small circulator, people think the noise is normal because it's not quite as gravelly as the bigger pumps get. All right. But even on an inline circulator, you can cavitate if you've got a 90 right before the pump. So 10 pipe diameters on the suction side of a pump is important. If you cannot have the 10 pipe diameters before pump, and this is very common on large piping, all right? If you cannot have the 10 pipe diameters, you can have what's called a suction, right here, all right, or a suction diffuser. All right, so for some reason you're dealing with a large pump, you can't have type 10 pipe diameters, then you'll put what's called a suction diffuser on it. All right, and a suction diffuser just evens out the flow. It's basically like turning vanes for a pump. Okay, so if you cannot maintain that 10 pipe diameters before the pump, then you put in a suction diffuser on there. Pro tips, suction diffusers usually have a strainer built into them, and there's a strainer that generally needs to be removed after startup. So they'll put a strainer in there to collect any big debris so it won't damage the suction diffuser when you first start it up. And then you're supposed to take that mesh strainer out after the system's circulated for, a day or so, and then remove that permanently. And then there's a bigger strainer in there with bigger mesh in it that's permanent. So if you don't do that, a lot of times they'll end up clogged up. And what happens if the suction diffuser clogs up or the strainer clogs up? Your pump cavitates. So on end suction pumps, generally they don't do this 10 pipe diameter. They'll always have a suction diffuser before it. But if you don't have a suction diffuser, you need at least 10 pipe diameters before the inlet of the pump. On the outlet of the pump, when you come out of a pump, another flex connector is a good idea. What they're showing right here is a gauge so that you can read the pressure before and after the pump. That's nice, but it's really only needed on bigger systems. I wouldn't bother most of the time with smaller ones unless you just like adding stuff. Then you will have a check valve and a balancing valve and another shutoff valve. Sometimes, instead of having these 3 valves, if you don't have that, you'll have what's called a triple duty valve. A triple duty valve is 3 valves in one. It is a check valve, a balancing valve, and a shutoff valve. It's really only 2 valves. It's a balancing valve that can be used as a shutoff valve and a check valve, but it can serve all 3 purposes. Notice our check valve is after our pump. Our balancing valve is after our pump. And then we have another shutoff valve, primarily for service. You never balance a valve on the suction side, right? Because if you balance it on the suction side, it's going to cavitate. If you balance it on the discharge side, it's no big deal. We're just basically increasing the head that pump needs to work against. to get the amount of flow that we want, which is why we generally select pumps that have higher flow rates and can handle higher head than we actually need, because we can always balance that pump down. We can't balance it up, right? Unless you have a VFD, you're not going to be able to get any more performance out of that pump than the performance curve. And even if you do, it's probably not going to be good for it. So we always balance down after the pump. And the check valve after the pump is just generally a good idea in most cases. And then you go from there. So those are the and notice here, suction diffuser may be used instead of a Y strainer, and it replaces that 10 pipe diameters. And the strainer screen has to be cleaned prior to balancing the system. It's just their notes. This is just some typical detail I found online. But these are the parts that you will have associated with your pump a lot of the time. So that is that's pretty much it. Yep. I think that's all I wanted to go over for tonight. Any questions? No, not really. So you have your pump seals leaking because you're creating a negative pressure on the. Right. Well, I mean, that would be ideal. Normally, you have a net positive suction head you want, right? So, that tells me that either the piping before the pump isn't large enough to keep up with the pump, or the pump is oversized for the application, or some other design consideration wasn't there, or you're just not giving it enough time on startup. But right. Yeah, because you said you're normally dealing with glycol, right? So you're trying to fill up the system. So they haven't filled up the system with enough pressure prior to startup. I mean, you can look at a well, I guess it would be more work than it was worth. I was going to say you can kind of predict what your pressure differential is going to be by looking at the pump curve, but I think that's what you're, and this is something I actually don't need to do very often. So I would have to make sure I brushed back up reading this pump manual before I open my mouth, to be honest. But I think that's kind of the purpose of making sure you look at your net positive suction head before you start up a pump, is to make sure that you don't create a negative pressure on the suction side, because you not only run the risk of something like your pump seals leaking, because those things are finicky as they are. They're already finicky as shit. So so you're dealing with a finicky part of the pump and putting it in a adverse condition. But not only are you doing that, but you're risking cavitation, right? You're gonna start cavitating inside the pump, and you're gonna damage the impeller before it has time to even start a whole life. So, yeah, you definitely want to. I mean, generally, I don't start up a pump until I've got this system bled of as much air as possible and at design pressure. You know what I mean? And when you're dealing with dry coolers, I know a lot of times those pumps are, on the roof or something like that. So they're basically working under a very small amount of pressure anyway, because you're at the top of the system where the pump is at. but you want to have that whole tank filled up and everything and try and get as much of the air as you're out as you can as you're filling, and then start it up. Yeah. Yeah. That is one thing you'll find. It's just like anything else. Bleeding air on one system is more of a challenge than the next one, and the best way to go about it is different than the next one. Or yep, every piping system has its quirks because it depends on who installed it. But some of the stuff we talked about last week, it applies to everything. Good piping practices of having grade on the piping for the entire length and grading up to your air vents and um, things of that nature. Just good piping practices make a huge difference on anything that has piping. But yeah, I've never dealt with it. But most of my pump experience, I don't have as much with dry coolers and stuff. Most of mine is boilers and chillers and cooling towers and things of that nature. I will tell you guys, um, we usually go through Baltimore Air Coil's design guide every year, at least as we talk about chillers and um, with cooling towers, you got to be really cognizant of where you put those pumps and how you pipe them off the cooling tower because you want to talk about a pump that can cavitate real fast. The pumps off the bottom of those cooling towers are usually pretty high volume and they're sucking the water straight out of the bottom of the pan, so they'll cavitate quicker than hell. But yeah, that's where most of my stuff is. I've only worked on a couple dry cooler pumps. They're expensive as hell because they're usually very high head, relatively low flow. As a matter of fact, I want to say that that's probably the highest head pressure pump I ever worked on was one for a Liebert thing. Right. Yeah, I want to say it was like I can't remember. I want to say it's like 200 or 300 feet ahead or something ridiculous. I'm like, Jesus criminy. It's $1,000 pump. Right. hmm What else you guys got? Hopefully, you'll find this useful at least once in your career because I'll tell you what, it's pretty satisfying when you've looked at everything else in the system, ruled everything out, and then you go, oh, the pump's too small. I got this. um, but it's not that hard of a process. Just save this at some point and keep it in your back pocket. And that way, when you need it, you know where to find the information. So if you guys are good, I'm good. You'll have a good evening. If you got any questions, stick around and ask the question. I never did open chat. So if anybody's yelling at me because of that, sorry. But no, I don't see any questions in chat either. So good there. Two man. All right. No problem, bud. All right. Nobody's got questions. I'm out too. Y'all have a good night.